All right, welcome back. Yeah, so what we just did is we just did your gas variables. We imagined you had a balloon, which you can totally go get a balloon if you have one in your home, or a packing balloon or whatever, and yeah, and poke it a little bit because why not? Get yourself a sense of what all these variables mean. You learn some new words, all these units that you've never seen before. Where we are going to next is here. So we're going to get you some ideas on kinetic molecular theory, including something we did not do last time. Kinetic molecular theory. What does this mean? You might notice that something that we talked a good bit about in the last video kind of meshes with one of these words. What does kinetic mean? Gosh, you can't respond. It's a video. Okay. Motion. Where did we talk? Okay. I won't ask questions of my answering machine. Yeah, motion. We're still thinking of all motion as a positive thing. And not in a value judgment kind of way, but in a numerical kind of way. We're not going to do negative motion. Yeah, so kinetic molecular theory has to do with the motion of molecules. Yeah, great. So the motion of molecules, and we in particular are going to be looking at gases. So it does change if you're looking at a different state of matter. So if you're looking at a liquid or a solid, the motion of the particles will be somewhat different from what we're looking at here. We are looking at gases. Oh, I don't know if I can screen share on a YouTube video. I will post a link for you. There's a visual that I plunk onto the board. Say, what do you see? What do you not see? I'm going to give you that link if you desire. Go ahead and click that link and make some observations of your own for a while. Usually we just throw these out, and this is the kind of day where you know virtually everything walking in that you need to. You just have maybe never written it down before. Yeah, there's 5 principles of kinetic molecular theory, which has to do with how gases behave. Off we go. Particles. I'm just going to give you these. Particles are in constant motion. Fast motion. It's something like 240 miles per hour or something. I don't know. Probably shouldn't give you numbers if I don't know them. But really fast. Like, air particles are actually moving pretty fast all around us. Should recalculate that. They bounce into each other. And I'll ask you, do they lose energy, gain energy, or keep the same amount of energy as they bump into each other? They keep the same amount. So they do run into each other. There are, we call them collisions. But they do not slow down, speed up. Some do slow down, speed up. On average, there's no change. Fancy word for that is elastic collisions, which is the net energy is there's no net gain or loss. Of energy when particles collide with each other or the walls of the container. So it's like bumper cars where you don't even need the gas pedal, because bumper cars exist in an environment with friction, and we essentially ignore friction when we're looking at gas particles. They're so small, that's another thing, they're small, that we functionally ignore any loss of energy from a collision. this is not entirely true. AP Chem, we will get into like ways in which this is not true, but for here, we go through the entire, and even when you get to like, we call them real instead of ideal, everything is still based on this ideal, that's just the word we use for it, the ideal scenario where elastic collisions are like actually completely elastic. Okay, moving on. So there's, what this means, there's no net gain or loss of energy when particles collide. Even though it's not complete, like, this is not the end-all be-all of our knowledge about gas, it's a pretty close approximation for a lot of things, actually. Particles are small, and with that, there's lots of space in between them. So when I give you the simulation, you're going to see a bunch of particles in a container. That's actually not like valid at all. In that size of container, you would have like a single particle drift in and out like occasionally if it was like showing things actually to scale, which is a much less interesting simulation. So the simulation you're going to see actually has way less space in between particles than would be true in like an actual kind of context. 5 principles, what else? Constant motion, fast motion, elastic collisions, particles are small, lots of space in between. I think that's all, actually. I think I usually put constant and fast as separate things. Oh, I knew I should have checked. I know there's one more. Might have to do with pressure on the sides of your container. It's like